Dimensional analysis and similarity are very powerful tools in science and engineering. Before we use them, though, we need to appreciate the law of dimensional homogeneity, which states that every additive term in an equation must have the same units. In other words, you can't add apples and oranges. Consider Bernoulli's equation, for example. Static pressure P is a force per unit area with dimensions of mass over length times time squared. The dynamic pressure, 1/2 rho v squared, has to have the same dimensions. Adding the hydrostatic head z doesn't work because it isn't dimensionally consistent. However, we can instead express the head as a pressure, rho gz, and now it is consistent. Of course, the Bernoulli constant, or total pressure, must have the same dimensions of mass over length times time squared as all the other terms. This basic requirement of dimensional homogeneity naturally leads to a set of non-dimensional parameters that describe all sorts of fluid phenomena. By understanding the role of these non-dimensional parameters, we can learn a lot about fluid phenomena without actually having to solve the equations of motion. There are a lot of these non-dimensional parameters, but the most important one in fluid mechanics, which comes directly from non-dimensionalizing the Navier-Stokes equation, is the Reynolds number. It's defined as the ratio of the inertial force to the viscous force on a body, and it's equal to rho VL over mu, or just VL over nu. When the Reynolds number is much less than 1, as in this bead falling through shampoo, the flow is dominated by viscous effects. We call this creeping flow. When it's much greater than 1, as in the case of this airplane, the flow is dominated by inertial effects. The Reynolds number is named for that great father of modern fluid mechanics, Osborne Reynolds. Another very important non-dimensional parameter is the Mach number, named for Austrian physicist Ernst Mach. It's defined as the ratio of the speed of a flow, v, to the speed of sound, c, and it determines a flow's compressibility. For example, cars usually travel at speeds less than 1/10 the speed of sound, where we ignore any small density changes and consider the flow to be incompressible. On the other hand, some flight vehicles break the so-called sound barrier and fly at supersonic speeds, or Mach number greater than 1. When the Mach number is around 1, as in this transonic wind tunnel test of a space shuttle model, small speed changes make a big difference in the flow pattern. This leads us to the powerful concept of similarity. We can test a scale model of a commercial jetliner in a wind tunnel, for example, and expect to get results similar to those of the full-scale aircraft, so long as we make sure that the Reynolds and Mach numbers of the model match those of actual flight. A lot of wind tunnel testing, and nowadays CFD as well, go into the design of a commercial jetliner. For many flows at low speeds, Reynolds number is the only important dimensionless parameter. As long as we match the Reynolds number of the model to that of the prototype, model testing can even be done using different fluids. For example, we can study the flow over a golf ball in a water tunnel, or the flow over a submarine in a large wind tunnel. Depending on the Reynolds number, some flows have different regimes with different flow patterns. The classic example is the flow over a circular cylinder, illustrated here using a soap film tunnel. At low Reynolds numbers, between about 4 and 40, attached vortices form behind the cylinder. Above about 40, we see the famous Kármán vortex street, the alternate shedding of vortices from one side of the cylinder and then the other. This is named after another father of modern fluid mechanics, Theodor von Kármán. A CFD solution also shows Kármán vortex shedding in the same Reynolds number regime. Finally, when the Reynolds number reaches values above a few hundred, turbulence begins to dominate the flow pattern. Another dimensionless parameter, the Struhl number, gives a non-dimensional frequency for such periodic flows. On the other hand, some flows don't change very much over a huge Reynolds number range. Here we've generated a toroidal vortex ring by injecting milk into a small aquarium at a Reynolds number less than 1,000. The infamous mushroom cloud from an atomic explosion is a similar physical phenomenon, only here the Reynolds number is at least several billion. Fluid dynamic similarity between the two is obvious by visual inspection. In liquid flows with free surfaces, the Froude number compares the speed of motion to the natural speed of gravity waves. A ripple tank demonstrates motion with a Froude number less than 1, equal to 1, and greater than 1. In the last case, surface disturbances are left behind, forming swept-back waves. This duck is swimming at a Froude number greater than 1, producing a similar wave pattern. There's a strong analogy between these liquid surface waves and shock wave phenomena in supersonic gas flow, where swept-back waves occur when the Mach number is greater than 1. The Froude number is also important in open channel flows, such as the spillway downstream of a dam. In this experiment in a water channel or flume, the fast-moving supercritical flow downstream of the spillway causes erosion of the riverbed. In this flow, the Froude number is the most important dimensionless parameter to match between the model and the full-scale spillway. The Reynolds numbers don't match, but it doesn't matter. Although we usually think of models as being smaller than prototypes, there are cases where it's more appropriate if the model is larger. It's hard to study the aerodynamics of a real fly, for example. It's just too small. Instead, a set of mechanical wings is tested in a tank of mineral oil. This mechanical fly is 100 times larger than a real fly, and its wings flap 1,000 times slower. So even though the dimensional size, frequency, and even the fluid are different, dynamic similarity is nonetheless achieved by matching the Reynolds number, the Struhl number, and a third parameter known as the reduced frequency. The Mach number is very small in this flow and is not an important parameter here. In this CFD simulation of a fly in flight, the actual scale and frequency of a real fly have been used as boundary conditions. It shows the vorticity being shed off the flapping fly wings. The scaling of the simulation is 1-to-1 with the actual fly, so all the dimensionless parameters are automatically matched. However, there are situations in which scale models are tested with CFD, like this simulation of waves hitting an oil platform. It was set up to predict a model scale flow in order to compare with data from an experimental model test. Here's another example in which a model race car is simulated as it would be tested in a wind tunnel in order to compare with scale model wind tunnel data. But sometimes actual race cars are tested full scale in large wind tunnel facilities, guaranteeing that the dimensionless parameters of the test match those of the race car on the track.